Section 9.4, calculating angles between lines and planes, between two planes. So you could have between line and plane, between two lines, you could have it between two planes. So we'll consider those situations. So if you have two lines intersecting two lines, they have to intersect, then to find the angle, you are going to, from the information that is contained within the equations of the line, you can only find an acute angle, because you don't really know, if you don't consider that, you might be finding an obtuse angle over here. So that's why the questions normally will ask you for an acute angle. So to make sure that you are always looking for an acute angle, you are going to do the dot product where A and B, so A and B are direction vectors of the two lines, and you're just going to, if the dot product appears to be negative, you change it to positive, so you take the modulus of that result of the dot product, and that way you always find an angle that's acute. So I'll show you how to do it. You've got two straight lines, okay, and you could see that they've been asked to find an acute angle theta between the two lines. So you straight away, you don't need to draw anything, you're going to do cos theta, and you're going to use, if that's your A and that's your B, or D1, D2 for direction vectors, you're going to use the formula for the dot product, for the scalar product. So we're going to have 3 minus 8 minus 1 dotted together with 2, 2, 3 over the lengths of these two vectors. So 3 squared add 8 squared add 1 squared, square rooted, multiplied by 2 squared add 2 squared add 3 squared. So 3 times 2 is 6, minus 8 times 2 is 16, minus 1 times 3 is minus 3. But be careful, it's better maybe to write it as products first. And this one here is going to be 10 plus 64, so root 74. And this is going to be 8 add 8 add 9, which is root 25, that's correct. So let's just do that, minus 13 over square root of 74 times 5. Okay, so you can see actually I kept the modulus signs out of this example, because what you could have done, you could have done cos inverse of that, and you will come up with a negative answer. So it's minus 68.5 degrees to 1 decimal place. Okay, I spotted the mistake. So it wasn't 25, it was, I can't add, 9 add 8 is not 25. So 9 add 8 happens to be 17. So this one here is 17. Apologies. Now, if you did not put modulus, which turns this into a positive value, then you would have done cos inverse of that value. There you go, and that will be square root of 17 111.5. So this is an obtuse angle. So you were asked to find an acute angle. So these are the two lines. There you go, and you found that angle. So you would have to do 180 minus 111.5. So you do 180 minus ans, which is 68.5 rounded to 1 decimal place. But really just learn So it's not the end of the world as long as you get to the final answer, so do a drawing. Best to learn this with the modulus. There you go. And you can even put the modulus there, and then you put this into the calculator, and you are going to get, I'm going to turn it into positive, but you can use the absolute value key on the calculator. There you go, 68.5. I just think it's nice to know where it comes from, that modulus. Okay, so 9.4, we're going to look at, was that example number 18? Yeah. Okay, so before, yeah, we've got a few examples before the next exercise. So the next idea is scalar product. Form of the equation of a plane. Actually, it is quite an intuitive thing. If you think about this, just having learned what a scalar product is, the dot product, the quicker version, what would it look like as a product of two vectors? So to get ax plus by plus cz, you may have had vector a, b, c, which is our normal vector, dotted together with a general point x, y, z, and you must have had answer of d. Now, that's just normal vector times, now this here, you could just write a general point r. R is a general point x, y, z, and that's equal to some value d. Now, if you know a particular point on a plane, so if you know that point P with the coordinates x1, y1, z1 is on the plane, then to find the value of d, you would just substitute these coordinates into this left hand side, i.e. you would substitute it into this. So you would find d to be a, b, c dotted together with x1, y1, z1. So that is very important, but obviously you can just substitute it. So another version of this would be normal vector dotted with a general point is equal to the your normal vector dotted together with the little p. So if you say that little p, which is position vector of OP, is that vector here. Okay, so let's have a go at example 19. We've got plane pi passes through the point A with a position vector 2, 3, minus 1, minus 5, and is perpendicular to the vector n, and we've got vector n. Find an equation of the plane. So this is really quick. You're going to write it down as we want vector equation, an equation, so of both Cartesian and scalar product form. This is, by the way, called scalar product form. Okay, so scalar product form is going to be your vector OA, so it's 2, 3, minus 5, dotted together with the general point, so R. There you go. And that's equal to D. Now D is simply 2, 3, minus 5 dotted together with the point 3, 1, minus 1. Okay, so D is going to be 2 times 3, which is 6, plus 3 times 1, which is 3, plus 5, which is 9 out 5, which is 14. So it's 2, 3, minus 5 dotted with R is equal to 14. So that's the scalar product form. And we will look at the dot product, sorry, Cartesian form. It's really pretty much replacing your R with X, Y, Z and doing the dot product, or sticking the normal vector components in front of X, Y, Z. And that's the answer. Okay, 2 more examples. So let's have a go at example 20. Okay, so example 20. Line L is given, and we've got a pi, so the equation of the plane, and we need to find an angle between the line and the plane. So let's just do a little sketch. So here's the plane, and there is the line. So the idea is to actually find an angle, to draw the normal from a point on the line to the plane. There we go. Now this normal here, normal vector, is going to be parallel to the perpendicular vector 2, minus 2, minus 1. That's our normal vector. Okay, now, so that's the information that we've derived from looking at the equation of the plane. Now, what else do I know about the line L? Well, I know that there is a direction vector of that line, and that direction vector, let's call it D, is going to be equal to 3, 4, minus 12. Right, so what am I going to do? Well, I've got 2 vectors, so what I can find, now in case the direction vector or normal was facing a different way, I am going to find the acute angle by doing the modulus of the dot product. So let's find the acute angle theta. There you go. So let's do cos theta is equal to, and let's do the 2 minus 2 minus 1 dotted together with 3, 4 minus 12. Let's do the modulus of that. And then this one here is going to be 2 squared add 2 squared add 1 squared times 3 squared add 4 squared add 12 squared. So 2 times 3 is 6, minus 8 and plus 12 over square root of 10. And this one is going to be 144 at 16 is going to be 169. That was 9. So these are nice square numbers. So it's 18, so it's 10 over 3 times 13. Over 39. Okay, so now thinking about the angle you can either use this information to find the angle between the plane, because the angle between plane is that angle, let's call it alpha. So if you do theta is equal to cos inverse of 10 over 39, then your alpha is going to be equal to 180 minus 90, which is 90, 90 minus theta, 90 minus theta, which is 14.9 degrees if you work it out. Now, another way of thinking is to actually think about this angle here. Your cos theta has to be equal to sine alpha. Okay, so if your cos theta in this situation must be equal to sine alpha, because if you think about it, cos theta, you've got adjacent over hypotenuse. If you look at the same ratio from alpha point of view, that side over that side would be its opposite over hypotenuse, therefore sine. So this way you could have just put sine alpha, which is equal to your cos theta, is equal to this formula, which leads us to introducing you to another formula, general formula for an acute angle theta, let's call it theta this time, between the line, which has a general equation r equals to a point plus lambda directions, and the plane written scalar form equals to k, and that's going to be your sine theta. It's got to be a modulus because we're looking for positive answer. It's going to be b, which is direction vector, dotted to go with the normal over the length of b times length of normal. There we go. So we've used normal and the direction vector. You don't need to use this formula. You can just do a little picture, find the angle between the two directions, so the normal and the direction, and then do 90 minus that angle. Good. Okay, so let's just now have a look at the next example, which is the last example, I hope, yes, before exercise 90. Hopefully you can still see it well. Okay, so example 21, you've got equation of one plane and the second plane, and we're looking for an acute angle between these two planes. So the idea here is to actually let's just visualize those two planes. So we are going to assume that they intersect each other. So there is one plane, and let's have another plane. Just draw it there. That's what I do. It might carry on like this. Okay, so that's your pi 1, that's your pi, capital Pi 2. A bit of a mess, but never mind. Okay, so how am I going to find an angle between these two planes? So imagine if I draw a line there, there you go, that we're talking about this angle here, theta. Just do that. There you go. Now the way you're going to find this angle is actually imagining drawing the normals to both of those planes. So there's one which is n2, and there's the other one which is n1. And I'm going to actually do a bigger picture now. So what I've done here is I'm going to imagine just taking a picture of that slice here, if you slice it along theta here. So we are going to get there you go. This is part of plane 2, this is part of plane 1, and we're going to draw the two normals. So we're looking for this angle, there you go, but what we have got is two vectors, and we are using the dot product. We can find an angle between those two vectors. Let's call it alpha, or let's call it theta 1, and that's theta 2. There you go. So if I can find what this angle is, then I should be able to find this angle very easily. There you go. So let's see how it works with our example. Okay, so let's find the theta 1, and then by considering the shape, the fact that these two angles are 90, let's find what theta 2 is. So all I'm going to do is find what cos theta 1 is. So this is going to be the dot product of the two normals. There you go. So it's going to be, let me just do it on this clean piece of paper. Let's do it again. So we have cos theta 1 is going to be n1 dotted together with n2. So let's find the angle between the two normals first. So the n1 is 4 minus 7, and n2 is 7 minus 4. So here we've got 4 squared, add 4 squared, add 7 squared, and this one here is going to be 7 squared times 4 squared times 4 squared, exactly the same. Okay, so here we've got 4 times 7, which is 28, 4 times 4 minus 16, and then minus 28. So that gives me minus 16. And over here we're going to have 4 squared, add 4 squared, add 7 squared, 81. So it's minus 16 over 81. So theta is going to be cos inverse of that value. Cos inverse of minus 16 over 81, 101.39, so it's 101.4. There you go. So that was our theta 1. So theta 2, so think what we had here, we had like a sort of a kite. It was a kite, well, not necessarily, but yeah. This here is 101.4. This is 90, this is 90, so this needs to be, these two need to add up to 180. If altogether you want 360, so you're going to have 180 minus 101.4. 78.6 degrees. Okay, let's go to exercise 9D.